Okay. So the main point with what we're going to talk about today is like how do we go from Lagrangian mechanics, which is a system of like second order differential equations. So I mean let's just run through the example of a pendulum really quickly once again. So in this case, so we have a pendulum. Right? So say it's pivoted like here, for example. It has, and this is like theta, this is L. Its x position is given by L sine theta, and its y position is given by L cosine theta, which means that if I take derivatives using like chain rule, we get something like this, which means that v squared is x dot squared plus y dot squared, because we're using like, the standard metric and whatever.
Yeah.
So you get L squared theta dot squared. And so the Lagrangian is given simply by 1/2 m L squared theta dot squared. Um, I mean, technically v squared would include this m 1/2 m term, but I don't really care about that. Plus mg L cosine theta. And now the equation of motion that we derived previously were d by dt partial L partial theta dot equal partial L partial theta. And if you write this out, this reduces to theta dot equals negative g over L cosine theta. Okay, so now the thing with Lagrangian mechanics is that this is a second order differential equation. Um, and the usual technique to solve second order differential equations is to write it out as a system of first order differential equations. Um, so when Hamilton looked at Lagrangian mechanics, he thought instead of just having a second system of second order differential equations, what if you just started off with a system of first order differential equations, right? Um, and in doing so, you have sort of already eliminated one step and you hopefully get a physically equivalent theory, right? So let's just write out like, what the problem actually is here. So the problem here being that, you get system of second order differential equations. Those are kind of hard to solve, and the usual techniques involve just bringing them back to first systems of first order differential equations. Hopefully you've seen how to solve systems of second order differential equations.
Yeah.
Yeah, yeah. I mean,
You
and
literally just make B a variable and have it be part of your phase space.
yeah, yeah. So now we're gonna, and the thing is that idea, I'm not exactly sure who came up with that idea. I wouldn't be surprised if it was Hamilton. Um, but we'll definitely try to bake that idea into our theory. So,
I
um,
mean, I'm not. Could it have been someone before? Because like that idea seems like the type of thing that even like Newton might have come up with. No, in theory,
I
I don't
mean,
know.
like possibly. I don't know. I don't really know much of the theory of differential equations because,
I mean, I don't know. The history doesn't really matter.
yeah, like I honestly don't know. Like one funny thing I do know is that Hamilton came up with Legendre transforms completely independent of Legendre because even though Legendre transforms were decently well used before Hamilton, so I don't know. Anything could happen really. But okay, let's so so let's see. So we have a Lagrangian, right, which is a function on the tangent bundle, and it returns a real number. And we get equations of motion, equations of motion, using the Euler-Lagrange equations, right? Which is basically the geodesic equations. Well, the geodesic equations are a specific example of the Euler-Lagrange equations, but you know, um, but
I
these
mean,
are
what
a
are
second
the
order.
sorry?
So yeah,
What are the other Lagrange equations? I haven't come across them before. I mean, I've
yeah,
heard of them, but like
yeah,
I don't
yeah.
know
I'll write
precisely
them
what they
down.
are.
The Euler-Lagrange equations. So Euler-Lagrange is d by dt partial L, I guess partial L partial Q dot, QI dot equals partial L partial QI. So if you have like a chart on your manifold with coordinates Q, these induce a chart on the tangent bundle given by Q and Q dot. And then in those coordinates, the Lagrange equations are given by this. And as you can see, like up here, for example, it's clear to see that these will be second order in the position because of this term. Okay.
Yeah.
So let's sort of now run through the argument that Hamilton was doing. So classically, we know that the Lagrangian is simply given by um, one second, sorry, Hamilton's idea. So classically, the Lagrangian is just, the kinetic energy minus the potential energy. Now what we can do is we can look at this kinetic energy term and sort of do some manipulations on it to see, what we can get out of it. Another thing to note is that classically the kinetic energy is, a quadratic. In fact, it's homogeneous. Um, so note K is homogeneous of degree 2. And basically what this means is that if I give it T in, I just pull and I can pull out the T and get a case make it like a T squared. Okay. Um, and now what we can do is we can utilize Euler's theorem for homogeneous functions, which will basically say that um, 2 times K is the same thing as Q dot QI dot partial K partial QI dot. If you haven't seen like Euler's theorem of homogeneous functions
I
before,
think we had to prove it for a PISA on 25 and 254.
yeah,
I'm
I mean,
pretty
I
sure.
wouldn't be surprised because this is actually a crucial step in deriving like the general form of the kinetic energy classically as well. Um, so it's it's a very important theorem that you should keep in mind, especially when you're doing like math related to like classical mechanics to some extent. Um, okay. So what we can do now is let's look at the differential of K. And this is, just writing it out, it's just this differential one form. And now what we can do is we can use Euler's theorem of homogeneous functions, um, and like sorry, and we can like differentiate this as well, right? So if we differentiate this, what do we get? We get 2 times dk is partial k by partial qi dot dqi dot plus partial qi d of partial k partial k dot.
And we're differentiating by the exterior derivative as well,
Yeah,
I think.
yeah. You're just
Okay.
taking the exterior derivative, and remember k is a function of like, positions and momentum, but then you know that like generally k is just 1/2 mv squared, like classically. And so it's independent of position. And so you get no like positional um one forms in this case. Like even this term will not have any positional one forms. Okay, now we have an expression of dk and we have an expression for 2 times dk. So what we can do is we can just take this, subtract them and see what we get. So if we do, so subtracting, right, you get dk is equal to, okay. So one thing to note is that this term and this term cancel out, right? And all you're left with is qi dot times d by partial k partial qi dot minus partial k partial qi dqi. but this thing is rather inconvenient. So what I'm going to do is I'm going to define new coordinates, call them pi, and they're just going to be these things. So let pi equal partial k partial qi dot. Okay. And what this reduces my thing down to is qi dot dpi minus partial k partial qi dqi. Okay. Does that make sense? Um,
Yeah, kind of.
I mean, I've just called this pi and just replaced it here. That's all I've done.
Oh,
Um,
wait, I see, I see.
Now I can use the fact that, you know, away from a critical point, this thing is, I can use like the inverse function theorem, right, to get the pi's in terms of the qi dots, right? Um, you should convince
Yeah,
yourself that like away from a critical point. Um, because at the critical point, it's sort of like qi and pi would basically be the same thing. They would both be zeros. So if you look away from that, you can invert this relationship at least in a small enough neighborhood using like inverse function theorem. So let's do that. And now, we can define k tilde to be a function of pi and qi, right? That's given by rewriting qi dot in terms of pi and subbing into k. Right, so basically we use inverse function theorem. We know that we can rewrite the p's, as we can rewrite the qi's in terms of the pi's using this function. And yeah, then we just sub it back in. So now we get a function of the pi's and qi's rather than qi and qi dots. Okay, does that make sense?
yeah,
Okay. With that, we can now, try to compare how like what this function does compared to like just k. And what we're going to do is we're going to take its differential. So, right, we're going to take its differential. And what are we going to see? We're going to see that this is partial k tilde by partial qi dqi plus dpi. Um, and now we see that if you compare like the coefficients of the differential forms, we know that these form a basis. So that means that this thing and this thing must be the same. And moreover, we know that this thing and this thing must be the same. Okay. And now this is quite interesting because, okay, I mean, the second one is not really too interesting because that's sort of expected by the inverse function theorem. But the first one, you know, is interesting because it says that the functions are not exactly the same, but rather they're almost like inverted in some sense.
like up to sign, it's like
Yeah, but up to a sign they're the same. That's good. Yeah. So what we get is we get a relationship between the QIs and the PIs. So firstly, we get that QI dot is partial K tilde by partial PI, and we get that partial K tilde by partial QI is negative partial K partial QI. Okay. Now what we're going to do is we're going to make an assumption on what the potential energy could be. So for now, we're going to just say, okay, the potential energy is just a function of position, not velocity. Um, Now you might say that this is a weird assumption to make, and I would completely agree with you because there are a lot of velocity dependent, like, energies, for example, like magnetic fields, for example. Um, but let's simplify our life a little bit initially. Like once we develop a momentum independent theory, if we add in momentum, if it works out the same way, then like what's the issue with that? Um, so for now, assume U is independent of PI. So what this now means, so what this now means is that if I look at this equation, I can add in a partial U partial PI, right? Because that's zero. So we can add that in and we can now define a new function. So Qi dot is nothing but partial K tilde partial Pi plus partial U partial Pi, which is nothing but partial H by partial Pi, where H is equal to K tilde plus U. Okay.
And I changed the Hamiltonian in this.
Yeah, and this function right here is called the Hamiltonian. And if you remember from my talk yesterday, this should be familiar because this was the first Hamilton's equation, right? This is dp, say this is dqi by dt equals partial h partial pi. Um, so okay, the derivation is not that bad. Um, let's now do something else. Let's now try to figure out like what the so okay, we now know the evolution equation for the position. Let's see if we can use this new h to find the evolution of the momentum. So we know that pi dot is nothing but partial L partial qi dot.
I mean, is there like a classical Mach version of like Adam First's theorem or like something else like that that allows you to tie like time evolution together with some like fixed quantity?
Sorry, what?
Not fixed quantity, sorry, but like some kind of like state function.
Oh, wait, could you repeat the question? I couldn't hear
Like,
you.
is that like a classical mechanics, like equivalent of Adam First's theorem, or like some like
Ehrenfest. Wait, I need to look up Ehrenfest. I haven't heard that in a
the
time.
thing where it's like the time evolution of like a system's like determined by like whether the Hamiltonian evolves in time, like whether there's an
Um,
energy
I
difference.
mean, yeah, that's exactly what we've derived here. Um, the only difference is that like now your expectation values are, you exactly know what your expectation value is. Um, so if you see like the statement of Ehrenfest theorem, like one of them says that the time derivative of the expectation of momentum is negative. Um, it's negative the derivative of velocity. I say a derivative of potential. But that's something that we can derive right now. Um, because in because Ehrenfest theorem is not really, I don't know, it is not really a profound statement for classical mechanics because it's exactly what we expect. Um, because we expect that it also just says that the time derivative of momentum is force, which is just Newton's equation. So Ehrenfest theorem is not really that profound for classical mechanics. I mean, if you take Newtonian mechanics as like a starting point, Ehrenfest theorem just reduces to Newtonian mechanics immediately. It's more interesting in quantum mechanics because now you don't really know what your momentum is, right? I mean, I guess you could know what your momentum is, but like you have some like uncertainty in what the momentum is. But it still says that the expectation values follow Newtonian dynamics. Does that make sense?
Yeah, I mean, I can believe that.
Okay. Um, okay. So one second, I have like a really weird mistake in my notes, which I don't really know how to rectify, unless it's not a mistake. Hold on. Why do I have an L there? Okay, all right. Let's see. So, oh yeah, okay. So we know that this is true. Sorry, we know that this is true. Sorry, it wasn't even a mistake. I'm just stupid. Um, but this is just, the left-hand side of the Euler-Lagrange equations, which I erased for some reason. Um, but this is just the Euler-Lagrange equations, right? But we know that the Lagrangian is given by um, K minus L. Oh, sorry, K minus U. And now we can use this thing we derived up here to replace this partial of K with respect to Qi with a partial of K tilde. And so we get negative partial K tilde, partial Qi minus partial U, partial Qi. But using linearity, we can just rewrite this as partial H, partial Qi. Okay. So what this tells us is that now using this transform of rewriting velocity in terms of momentum, we've basically reduced a system of second order differential equations into a system of first order differential equations, because these are first order, right? System of first order differential equations. Um, but now we have twice as many equations, um, which is fine, which is whatever. Um, are there any questions on this so far?
I mean, I guess what are the advantages of like doing it this way as opposed to just like having your X and your V and having two other systems of uh first order differential equations anyway?
What are the advantages of doing it this way? Okay. So one of the things we'll see like pretty soon is that doing it this way leads more naturally to the fact that you don't necessarily care about the differential equation as much, right? You more so care about like flows of vector fields. Um, you could also look at that from a second order differential equation point of view, but it's more natural to look at it in a system of first order differential equation. Um, Another thing you get out of this is it's an equivalent theory to Lagrangian mechanics. Well, it's not too equivalent because it relies on the invertibility of this thing. Um, but you get another theory of classical mechanics that that works basically all the time as well. And it just turns out that, Hamiltonian dynamics um, is a more natural place to look at when you want to describe things like quantum mechanics, for example, right? Because momentum is somehow a more, um, how do I say this? So it turns out that like momentum is,
Somehow more sort of essential than masses or the
yeah,
velocities
yeah,
on
yeah.
their own.
So it turns out that like momentum is a more essential quantity than velocity is. Um, because like as Einstein described, momentum fits into like a four vector. If you've heard of that before, it fits into like like E equals mc squared, right? It fits into E equals mc squared a lot nicer, for example. Um, and yeah, momentum is just a nicer quantity to work with a lot of the times than velocity is. Um, because you can actually measure momentum because it's related to energy. Velocity is like not as related to like energy as we think it is. But okay, good question, good question. Um, the only issue we have so far now is like how do we even compute what H is, right? Um, that's an issue we have. So let's now try to see how to compute H. Because okay, classically, like finding L was really easy. You just take kinetic minus potential, and there we go, you're done. But how do you do that with H? So note H is Let's define something called L tilde, which is just, you know, L, but a function of P and Q. But L is nothing but K tilde minus U, which is the same thing as K tilde minus H plus K tilde, right? Um, because U is uh, K tilde plus U is H. So if you rearrange this equation, you get this. Um, and what that tells you is that L tilde plus H is equal to 2K tilde. Now we can use Euler's theorem of homogeneous functions again and get the following, right? Which then allows me to solve for like that. And now we can rewrite H in terms of L tilde and all the other things. So we get H is just Qi dot Pi minus L tilde. Now, if you've taken a course in thermodynamics, this should be familiar to you because this is the Legendre transform.
Yeah, we didn't. I don't think we did the Legendre transform explicitly in 252. I mean, we were
Okay.
kind of surrounded by the byproducts of the Legendre transform,
Yeah, I
like all
mean,
the
Legendre
product
transforms are
previously.
quite nice because you know the four fundamental quantities of thermodynamics, like Gibbs free energy,
Yeah,
um, internal energy, so on and so forth. You can,
Helmholtz
they're just,
and
yeah,
yeah,
Helmholtz. They're just Legendre transforms of each other. Um, so you can literally go back and forth between them by Legendre transforms. So the Legendre transform is quite nice. Okay, so now we have a procedure on how to, describe the Hamiltonian. We've seen what the Hamiltonian is. We've seen the equation of motion. So let's use all of this together and let's now like do an example, right? Let's do an example. So example, let's do a simpler example than we did before. Let's look at a harmonic oscillator. So for a harmonic oscillator, the kinetic energy is just 1/2 mx dot squared, and the potential is 1/2 kx squared, but we put a minus sign, so it's 1/2 kx squared like that. Um, and now we know that the momentum is partial L partial x dot, which is just what like mx dot, which is nice, right? This is like classically, this is what we call the momentum, right? It's just mv. So it's good to see that, okay, Hamiltonian mechanics has given us mv. Moreover, um, I need to now rewrite x dot in terms of p because I need to sub it back in here to get L tilde. Um, so what you get is that x dot is just p over m, and so x dot squared is just p squared over m squared. And so L tilde is just 1/2 m p squared over m squared minus 1/2 kx squared, which is just p squared over 2m minus 1/2 kx squared. Okay. We can now use this to find the equation of motion. So for example, we know that x dot is simply partial h partial h partial p, which just gives me p over m, which makes sense. And then we know that p dot is negative partial h partial x, which is kx, which also makes sense. So, okay, this is nice, right? We get um, these equations of motion should be very familiar, right? So it's very good to see that we're getting these things back. Okay, are there any questions so far?
not really.
Okay. Um, It would be instructive to like take your favorite system, like classical system, um, and solve it three ways. Solve it using Newtonian physics, solve it using Lagrangian physics, and then solve it using Hamiltonian physics, and then just choose which one you like the best. Um, we will see shortly that like actually I'll just tell you this. So if the energy of your system is conserved, um, if the energy of your system is conserved, then your Hamiltonian is simply the kinetic energy plus potential energy. Um, Actually, sorry, wait, I'm sorry, I confused the things up. If your if your kinetic energy is quadratic in velocity, then your Hamiltonian is simply your kinetic energy plus your potential energy. If um if energy is conserved, then the Hamiltonian is the total energy. That's what I meant to say. Sorry about that. Okay. Now, even like as long as things remain invertible, remember in the regimes we were working with, we need that like, certain expressions were invertible. All the things we've talked about make sense even if the Hamiltonian is not kinetic energy plus potential energy, right? Because we derived this equation right here, right? This equation right here defines the Hamiltonian, right? So you don't even care about invertibility. Sorry, you care about invertibility because you need to rewrite certain things, but you don't really care about whether Hamiltonian is kinetic plus potential, right? This we can now sort of take this to be the definition of the Hamiltonian. So if you're given a Lagrangian, you can define this object to be define it to be the Hamiltonian, which in situations where like energy is not conserved is actually different from the total energy. Um, okay, so what we can do now is if we assume L has no explicit time dependence, then you know that dl dt is nothing but by chain rule is excuse me dl by dqi qi dot plus dl by dqi dot uh, qi double dot, right? And now we can use the Euler-Lagrange equations. Um, we can use the Euler-Lagrange equations to get q. Sorry, this should be qi. No, no, no. Sorry, I was right. We can use the Euler-Lagrange equations on this guy to get d by dt partial L partial qi dot plus um, qi double dot partial L partial qi. But now, if I look at this carefully, this is just d by dt of qi dot partial L partial qi dot, right? So what this is telling me at the end of the day is that d by dt of qi dot pi minus L is zero, right? And if you remember, this is Hamiltonian. And so in other words, if there's no explicit time dependence in your Lagrangian, then the Hamiltonian and the total energy then the Hamiltonian, um, firstly, it already coincides with the total energy because we've assumed, it's quadratic, but you also get that it's conserved, which is very good. Okay. Um, we can now, okay, yeah. Are there any questions? Sorry, this should be plus here. I just realized. Yeah. So are there any questions about like conservation of Hamiltonian in like independent, like time independent systems?
No, I mean it makes sense.
Okay. So let's go back to the harmonic oscillator. In this case, again, let me just rewrite this. So the Hamiltonian was given by 1 over 2m p squared plus 1 half kx squared. And x dot was p over m, p dot was negative k over x. And so we get a system of equations given by d by d dt. X p is nothing but 0, 1 over m, negative k, 0, x p. And then, we know the solution of this. This is just, we just exponentiate. Right? And then you can sort of, write out the matrix exponential using standard formulas to end up with,
The fuck ass infinite sum,
sorry, what?
the infinite something.
Yeah, yeah. You can use that to rewrite this as cosine of omega t, negative omega over k, sine of omega t, m omega sine of omega t, cosine of omega t, evaluated at x0, p0, where omega squared is k over m. Okay, so this is really nice because clearly we can now see that like energy level sets are like ellipses. Um, so that's cool. Um, okay, are there any questions about like this so far? Like this step right here is just like solving a differential equation. Sorry, excuse me. Solving a differential
Yeah,
equation.
no, that's like fairly.
Yeah, it's just a linear system of differential equations. Um, Looking at like mechanics this way is now nice because rather than like staring at a system of differential equations, it is more natural now. I mean, from this example, we can see it's more natural to look at the flow of vector fields, right? I hope that jump is not too abrupt because clearly, like if I solved this using like Lagrangian mechanics, I would have gotten something, but then it wouldn't be obvious to me that, I should look at the flows of ODEs. Does that make sense? Because in the
Yeah.
Lagrangian setting, like in the Lagrangian setting, I would have gotten x double dot equals negative kx, and I know how to solve this immediately. So I would have never even gone into a step where I needed like vector fields to begin with. Right? Um, and so it's quite like in this case we can see immediately that Hamiltonian mechanics gives us a new perspective on the same classical system, and now forces us to look at the flow of some vector field on the OD, like on phase space. Um, so this is now a good transition into the phase space. Okay, so phase space. Um, Phase space will have coordinates qi and pi. But the way the pi are defined, it's pretty clear that these are somewhat dual to the velocities, right? Because we're defining them in terms of the like partial derivatives of velocity. And so what we're going to do is we're going to take, hence we take phase space to be t star. right? The cotangent bundle, because these are dual to the tangent bundle, which is what Lagrangian mechanics was based on. That also justifies our use for lowercase indices for momenta. Um,
Wait, so what are you pulling the manifold back through? Oh,
uh,
wait, no,
so
that's the tangent. Oh, I see what you mean. It's the dual
yeah,
to the tangent space.
yeah. So basically,
Oh, I see.
we define a new vector bundle over the same manifold. But instead of the tangent space, we now take the dual space at each point. It turns out that they pretty much have the same geometry and everything, so it's not. Um, but tangent cotangent spaces are just sometimes nicer to work with. Um, okay, so with this out of the way, like I mentioned that we should now look at the flow of vector fields, but which vector field should we even look at? It should clearly be the vector field that, generates Hamilton's equation of motion when I try to find its flow, right? So, so if I look at Hamiltonian H and vector field XH given by partial H, partial PI, QI, partial H, partial QI, partial PI. Now, if I tried to solve for the flow, I would get that QI dot would be this thing, and then PI, sorry, yeah, QI dot, PI dot would be this thing, which is just Hamilton's equation of motion, right? Then flow solves Hamilton's equation of motion, right? Does that make sense?
Yep.
Okay. S- excuse me. So now what we've gotten, right, um, is that if we take if we take any function on the cotangent space, we've gotten an action essentially of this function onto like its space of like smooth functions. So we get an action of C infinity T star M onto itself by H gets mapped to XH, right? Since um like XH
Wait, an action like a group action.
um it may not be a group action. Um and the reason it may not be a group action is because of like chain rule. Um so I would write that out. Like when I say action, I just mean it acts on itself, like not in terms of group action. It just
Oh, I see, I see.
yeah, this is just a way to act on the space. It doesn't have to satisfy any group law because the space of smooth functions isn't even a group. Well, it's a group under addition.
That's what I was confused about it.
Um,
Yeah.
it's a group under addition, and yeah, so if you take the group law to be addition, then it is actually a group action. Um, if you just write it out, like because addition would just split these, so each one would pick up this own thing, and then it splits nicely. So if you want to look at it that way, then yeah, I guess I'll mention a Abelian action if anything. But what is this action, right? So XH of F is nothing but partial H partial PI partial F partial QI minus partial H partial QI partial F partial PI. But this should seem really familiar, right? This is just the Poisson bracket of F with H and F. So I'm going to define this bracketing operation to be this object right here. Okay. And another way we can write this is H maps into the bracket. Okay. One thing to note is that because of the chain rule on the partial derivatives, um, this thing is actually a derivation. So this is a derivation, which makes sense because again, it's defined by vector fields. Um, and antisymmetric. Okay. Hence, it is a biderivation. And what I mean by biderivation is that it satisfies chip product rule in both entries. I'll let you check out why that is. Now
But
another,
so derivation to something that satisfies the product of invariancy.
yeah,
Like that's
product
something.
rule and like linearity.
Yeah. Okay.
Um, So if you have some like you can think of like abstract like abstractly you can think about this. So say you have some algebra over a vector field. Um, Actually, just say you have some algebra over a field. And then a derivation on this algebra is a linear map that satisfies product rule, right? And now the algebra here you have is a space of smooth functions. So yeah. Um, okay, I have an exercise, and that is to check Jacobi identity. It's always fun to write out the Jacobi identity. Um, we'll see very shortly that there is a much faster way to prove this, but everyone should always do this derivation once. Um, it is very annoying. Anyways, so with all of this, I'll just define something called a Poisson bracket. So definition, let M be a smooth manifold. Um, a Poisson bracket on M is a map that takes in two smooth functions and returns a smooth function such that it is linear over R. Second is a biderivation. It's skew symmetric, um, or rather anti-symmetric. Three is a derivation, um, in an entry, and finally satisfies Jacobi identity. So the Poisson bracket we gave up here is just a specific example of a more general geometric structure called a Poisson bracket. Um, Poisson geometry is an interesting field, I think. Um, it's pretty fun. If you have any questions, you can ask me about it anytime. Um, so yeah, okay. Um, okay, so are there any questions about what a Poisson bracket is, what the Hamiltonian vector field corresponding to a function is, etc.?
Is the Poisson bracket the unique uh, like I don't want to say operator. I guess yeah. Like is it the unique operator such that like all those four properties hold?
It is
Or like
by
there's any like
far,
operator
it
factor through
is
the
not
Poisson bracket?
unique whatsoever. Um, for example,
But
if
is it like some kind of like universal thing? Sorry, yeah,
no,
go on. Sorry.
it's not unique because I could just take the Poisson bracket of any two functions to be zero, right? That gives
Oh
me
no,
a
no.
point.
As in like, is it the only operator that fulfills all those four properties?
No, because okay, so this Poisson bracket that I gave up here is clearly non-zero, right? It'll give me a non-zero function at the end, usually. But I could also define another Poisson bracket to be the zero map. right? It takes in two smooth functions and it gives me zero. It's linear, because obviously. It's anti-symmetric, obviously. It's a derivation, obviously. And it satisfies the Jacobi identity, obviously. So yeah, it could be zero. Another interesting one, in my opinion, is you could define um, x and y to be like x, right? And this would be um, a Poisson bracket that's different from this Poisson bracket. Because this Poisson bracket, um, so new, in the usual Poisson bracket, the Poisson bracket of x and y would be 1. And then you can actually show that any Poisson bracket on a two-dimensional sorry, any anti-symmetric biderivation is a Poisson bracket on a two-dimensional manifold. Um, and the proof sort of goes by saying that the Jacobi identity defines a three tensor, like an anti-symmetric three tensor, but any anti-symmetric three tensor on a two-dimensional manifold must be zero.
Has
So
to be the zeros. Oh, yeah.
yeah, so you could literally just take any you could take any anti-symmetric like derivation on a two-dimensional manifold and it'll be a Poisson bracket. So it is not unique whatsoever. It has no universality, nothing. It could be it could behave extremely badly. Like like local geometry of Poisson is even though the local geometry is very nice, um, when you break down Poisson geometry into like its fundamental objects known as leaves, the leaves may not be nice. Um, we can chat about like leaves like later. Um, because for that I'll have to define symplectic forms, which I'm gonna define right now. Um, it actually turns out that like Poisson geometry locally just reduces down to symplectic geometry. So that's nice. Um, well, it changes to almost symplectic geometry. Okay, good questions. Um, okay. Now what I can do is I can like, ask myself like, what do conserved quantities look like in this, right? Um, so if I have a quantity that's conserved, like how would I know that the quantity is conserved? So let's take f to be a quantity. Let f be, be a smooth function on t star m, then f is conserved. Um, f is conserved if and only if x h at f is zero. So basically, this says that like you can reduce questions about conservation into like, can you find things that are conserved along flows of vector fields? I'll let you check the details out for this one. It's very simple chain rule computation. If you have an arbitrary Poisson bracket, and you have a function that if I map into the Poisson bracket gives me the zero function, that is called a Casimir. So definition. So let M be a Poisson manifold if fg equals zero for all g, then f is said to be a Casimir. Yeah, it's called a Casimir function. Casimir functions are nice because uh, the way you can find the like leaves of a Poisson manifold are by finding all Casimir functions, and then looking at their like combined level set. Um, and this will give you like a bigger partition than the leaves, but then you can usually make an argument to say that okay, um, the level sets are like the level sets are the leaves. Um, okay. But okay, so with all of this, let's look back at like the differential of h. So we know that the differential of h is, well, very simple expression, right? Um, and now if we look at the Hamiltonian vector field associated to h, we see some similarities, right? In the sense that this thing is basic is how do I actually want to say this? So if I replace this with negative dpi and I replace this thing with dqi, right? I just get my vector field, right? So what this actually, so if we replace dpi with partial qi and dqi with negative partial pi, dh transforms into xh. Okay. And so, if we look at omega given by dpi wedge dqi, right? Then if I take xh and I put it into omega, what do I get? So let's see. So this q goes into here, so I get partial h partial pi dpi. This pi will go into the first component, so I get negative partial h partial qi d qi. Do I need a minus sign somewhere? That's the thing with this. A lot of these are like stupid conventions. Um, oh no, I just made a stupid mistake. This should be part negative, yeah. Okay, so it'll be this. dpi minus partial h partial qi. Um, dqi, right? But this is just negative dh. Okay. Are there any questions about these computations?
Not really, no.
Okay. Okay. Um, so let's now look at certain properties of omega. One thing to note is that if I take d omega, it's clearly zero, right? I hope that's clear to see. Moreover, if I take n wedge products of omega, I get n factorial times dp1 to dpn, dq1 up to dqn. And so omega is non-degenerate, right? Um, and if you remember like an exercise I gave you, omega should like M should be an even dimensional manifold, which is good. Does that make sense?
Yeah.
Okay. Now I will leave it as an exercise. Check that omega of xf and xg is nothing but the Poisson bracket of f and g. Okay. And use this to show that d omega equals zero if and only if the Poisson structure. Actually, show that d omega equals 0 leads to the Jacobi identity. So what we've done is we've taken like Lagrangian mechanics, we transformed it into a system of first order differential equations. We then introduced the Hamiltonian, which then led us to look at two new geometric structures, a Poisson bracket and like this differential two form, which now suggests like a very nice generalization of Hamiltonian dynamics. Um, so we can look at symplectic manifolds. So in definition, let M be a smooth manifold. Omega is a two form omega is called symplectic if d omega is 0 and omega is omega p is non-degenerate for all p and n. Okay. And exercise show M must be even dimensional. Okay. If omega is exact, i.e. d omega, omega equal negative d theta, we call theta a symplectic potential.
I mean, does the Poincare lemma still hold on M then?
No, right? The Poincare lemma does not hold always. For example, on the torus, Poincare lemma wouldn't hold. Um, on the
Well, no,
torus,
as in
d theta wedge d phi
like
is a
as in
symplectic.
if M was like a star-shaped set, so to speak, then like omega being closed, which I believe we know it is because
I mean,
If it's symplectic, then it's closed, and then it's exact.
if the cohomology of M is nice enough, you can always get that it's closed. Sorry, that it's always exact. Um, but you might not have that nice geometry. Like for example, on a torus, um, like I said, d theta wedge d phi is a symplectic form, but it is not exact. So yeah. Okay. Um, so yeah, I mean, this is a nice place to leave off, I think. Next time what we'll see is that the cotangent bundle has a canonical choice of symplectic form. Okay. So the cotangent bundle will always have a symplectic form. Um, Wait, and it gives one of my favorite proofs of orientability of the cotangent bundle. So no matter what the manifold is, the cotangent bundle is always orientable. And that's because it has a symplectic form. And since it has a symplectic form, it must be diffeomorphic to the tangent bundle, which is also then orientable. So tangent bundle and cotangent bundles are always orientable. And I don't know, I think that's like a pretty neat fact. Um, so yeah, are there any questions?
Uh,
Okay, if there are not any questions, I'll just end the meeting here. Hold on.